Welcome to tutorial number 14 on semiconductors for the standard amateur radio course brought to you by the Radio and Electronics School. My name is Ron, VK2DQ. The self-test for this tutorial is drill number 11. We're going to be discussing semiconductors. However, in the standard syllabus there is no need for you to know the internal atomic operation of semiconductors. You only need to know the external operation. So for this drill I'm going to be going straight into the question set, because most of the questions you're likely to get in the assessment are ones based on basic symbols and very basic circuit identification. And by leaving out the internal operation, which you do not need to know, we're going to be saving you an awful lot of time. Let's have a look at section 11, semiconductors, and these are typical assessment questions, not the same, but very typical in format and content. The first question is about a diode. A semiconductor diode, or any diode, is a device that will conduct current in one direction only, and semiconductors are generally, not always, but most semiconductors are made of germanium or silicon. And for a diode to conduct in the forward direction from cathode to anode, the bias voltage, the voltage you apply with the correct polarity, must exceed this voltage before the diode will conduct in the forward direction. Now and this is something you just need to remember, if the diode is made of silicon, the forward voltage necessary, you'd have to put negative on the cathode, positive on the anode, to get current to flow from left to right, from anode to cathode. If it was silicon, it would be 0.6 of a volt. If it were germanium, it would be 0.2 of a volt. So the correct answer is germanium 0.2, silicon 0.6, and that is answer A. Here we've got the symbol for a diode. This end of the diode is called the cathode. And this end is called the anode. For a diode to conduct, negative must be placed on the cathode and positive on the anode, and that voltage must exceed 0.2 of a volt for germanium and 0.6 of a volt for silicon. And if you do exceed that voltage, there will be conduction in this direction from cathode to anode. On the actual diode, which looks just like a resistor without colours on it, one end of the diode is marked with a band. You won't be assessed on this. The banded end is the cathode. What you need to remember is the symbol, and you need to remember that to get forward conduction you must put negative on the cathode and positive on the anode, and that voltage must be greater than 0.2 of a volt for germanium and 0.6 of a volt for silicon, and you'll get conduction in that direction. You will not get conduction in this direction. So if you were to put negative on the anode, positive on the cathode, the diode will not conduct until you reach a extremely high voltage called the peak inverse voltage, because everything will conduct if you put a high enough voltage on it. And if you put the peak inverse voltage on this diode, which could be 200 or 300 volts or even more, it will conduct in the reverse direction and the diode will be destroyed. you need to remember peak inverse voltage. That is the maximum voltage a diode can withstand when reverse biased. Reverse biased is no conduction. Forward biased is when there is conduction. Question number 11.2. This question is related to the first question. This is a transistor. You're seeing the symbol here of a PNP transistor. If it was an NPN transistor, the arrow would be pointing outwards. If you think of the arrow pointing outwards, never points in, the arrow never points in, NPN. This is a PNP. But what we're being asked here is what it would be required to turn this transistor on to enable a PNP transistor or NPN transistor to conduct, and it's a silicon transistor, so that would be 0.6 of a volt, same as a diode. If it was made of silicon, it'd be 0.6 of a volt. I'll talk to you more about the transistor symbol later. Just for now, just remember that the base is the input, the collector is the output, and the emitter is the output. The emitter is common to input and out, and it is changes of base emitter current that produce a much larger emitter collector current. So if we change the the base emitter current by 10 milliamps, we could change the emitter collector current by 100 milliamps, and that would be an amplification of 10. So a transistor is an amplifier. Moving on to question 11.3. The forward bias silicon PN junction is considered to conduct at approximately, this is just testing your knowledge of silicon and germanium, 0.2 of a volt for germanium, 0.6 of a volt for silicon. So if we were to put negative on the cathode, positive on the anode, and if the voltage was greater than 0.6 of a volt, a silicon diode would conduct from cathode to anode, always against the direction of the arrow. The arrow points always against the direction of electron flow, so current would flow from cathode to anode, from left to right. Question 11.4, the amount of forward bias required to enable a germanium transistor to commence conduction. I've got a symbol of a germanium diode there, they look the same, and the question's about a transistor, but it doesn't change the question. The amount of forward bias to enable a germanium transistor to conduct is the same as a diode. It's germanium, so it's 0.2 of a volt, not 0.6, that would be silicon. So 0.2 is germanium. Oops, it'd be nice if I spelled it right there. And 0.6 of a volt is silicon, whether it's a transistor or a diode. Question 11.5. That symbol there is a varactor or varicap diode. And what a varactor or varicap diode is always reverse biased. It's never forward biased, and it acts like a variable capacitor. You can get a capacitor somewhere between about 30 picofarad and about 180, 200 picofarad by using a varactor diode, and they are always reverse biased. They are never forward biased, so they never conduct. It's the voltage across them, and there's a dielectric material inside them. I'm not going to explain that to you, but that gives us a voltage variable capacitor. So the answer to this is that voltage variable capacitors, varicap or varactor diodes, behave as capacitors when they are reverse biased. And you need to know that, and you need to know that varicap diodes or varactor diodes are used to change the effective capacitance in a circuit by varying a voltage. Let's go straight on to 11.6, which is related. A varactor varicap diodes are used in receivers for altering the effective capacitance of a circuit. If you had a tuned circuit of which a varactor diode was part, you could apply a voltage to that varactor diode and change the resonant frequency of that tuned circuit. Question 11.7. Varactor or varicap diodes may be used for, and we've already answered it in a previous question, but it doesn't hurt to drum it home. They change the effective capacitance in a tuned circuit. So it could be used to change the resonant frequency of a tuned circuit. You'd still have an ordinary capacitor and inductor in a tuned circuit, but you'd put a varactor in series with the capacitor, change the reverse voltage on the varactor, and that would change the resonant frequency of that tuned circuit. Question 11.8. A varicap diode is used for electronic tuning of resonant frequencies because it changes the capacitance in a circuit, therefore changes the resonant frequency. Let's have a look at 11.9. 11.9, and I've put a circuit here. I often put circuits here which you don't have to know or understand completely, but I do it to give you a little bit of background into varactor diodes. Now there's the varactor diode. In fact, there's two varactor diode there. There's a tuned circuit, an inductor and a capacitor in a tuned circuit. So that circuit has a resonant frequency, and by changing the voltage on that capacitor we can change the resonant frequency of this oscillator. This is a voltage controlled oscillator. So by adjusting the voltage coming from here to the varactor diode, we can affect this capacitance, and that affects the resonant frequency of that circuit, and that's our oscillator output. By the way, you don't need to know this, but that's a Colpitts oscillator, and I can tell that by the tap capacitance on the base of the transistor. So you don't need to recognise that circuit. It's only there to give you an idea where a varactor diode is used and how it's used. The answer to this is when the reverse bias is changed slightly. Varactor diodes are always used with reverse bias. Number 11.10 is just asking us what a varactor diode is. Well, it's a p-n junction diode. In fact, any diode can be used as a varactor diode if it's reverse biased. So it's just a p-n junction diode. The next question is about Zener diodes, and there's the symbol for a Zener diode, and this is a very basic power supply. Zener diodes are always reverse biased. Notice this difference in the symbol for a Zener diode. So this Zener diode is reverse biased, and they do conduct because it doesn't take much voltage to get a Zener diode to conduct. To make a Zener diode reverse conduct, you must have, in this case, must have greater than 8.2 volts because it's an 8.2 volt Zener, and you would put positive on the cathode and negative on the anode, probably about 14 volts here, and that diode will reverse conduct. It's not destroyed because it's got this resistor in series with it. That prevents the diode being destroyed when it is reverse conducting. What the Zener diode does for us is produce a constant voltage here depending on its breakdown level, in this case 8.2 volts. So we would get a constant 8.2 volts. So a Zener diode is a voltage regulator. And to answer the question at last, the Zener diode in this diagram would always be reverse biased. So your questions are not so much about applications, just a basic knowledge of whether they're forward or reverse biased and how much voltage is necessary to do that to make them work. I just want to talk briefly about transistors. This transistor is an NPN transistor because the arrow is not pointing in. Think of not pointing in, NPN. Not pointing in. The arrow is not pointing in, so it's NPN. If it was pointing in, it'd be PNP. Whether it's PNP or NPN, the three leads of a transistor are called the same. The input, where we put the signal in, is the base. The output is the collector, and the emitter is common to both the base and the collector. So if I drew a simple circuit here, very simple circuit, this would be the output, and this would be the input. A transistor amplifies by changing the base emitter current. If we change the base emitter current, we change the emitter collector current by a much greater amount. If it's a silicon transistor, we need at least 0.6 of a volt across the base and emitter to make it work. If it's germanium, 0.2. A big help in remembering how transistors work is remember that the currents, and there's only two, there's a base emitter current and the collector emitter current. The base emitter current would flow in this direction against the direction of the arrow, against the direction of the arrow in the symbol, and the collector emitter current or emitter collector current would flow in this direction against the direction of the arrow. So that would mean that that would have to be negative and that would have to be positive. And in this circuit, that would have to be negative and that would have to be positive. And for a PNP transistor, those polarities would be reversed because the arrow is pointing inwards like that. Because the emitter is common to both input and output, the name of this configuration, and you need to know this, and it's the only one you need to know, is common not a very good N, I mean, that is called common emitter. And that's the only one you need to know. There are others, we're not going to talk about them. But these are the ones, because the emitter is common to input and the emitter is common to output. So that's common emitter circuit. So the base is the input, the collector is the output, and the emitter is common to both input and output. That is called common emitter circuit. Question number 1112 is what I was just talking about with transistors. This is an NPN transistor, it's not pointing in, and they're asking us about whether the base and emitter or collector, whether they're positive or negative and so forth. So if we wanted current to flow against the arrow, this would have to be negative, so the base would be negative and the emitter would be positive, and the collector, which would be far greater negative than the base, and this would be positive as well. So the collector is more positive than the emitter is the answer. This would be positive, this would be negative. Current flows against the direction of the arrow, upwards from negative to positive. So the collector is more positive than, oops, wrong one. I do that sometimes. The collector is more positive than the emitter. (1113) A correctly biased PNP transistor will conduct when? Let's look at the symbol and forget about the answers for a moment. If if we want current to flow in the collector circuit, it would flow against the direction of the arrow. So this would be negative and this would be positive here. In the base emitter circuit, this would be negative and this would be positive for current to flow against the direction of the arrow. So let's have a look at the answers. So the collector is very negative, the base is less negative, and the emitter is always positive. So the emitter is more negative than the collector, that's wrong. The collector is more positive than the emitter, that's correct. So the collector is, I'm sorry, that's wrong. The collector is more negative than the emitter is correct. So you have a negative collector, a positive emitter, current will flow against the direction of the arrow. If you just remember current has got to flow against the direction of the arrow, you'll get all of these correct. I would suggest that in the assessment you draw the symbol and put the negative and positive on it to help you work it out. So the answer is D, the collector is more negative than the emitter. 11.14, the collector current of a bipolar transistor is controlled by the base current. It is the base emitter current, the small base emitter current, which controls the much stronger emitter collector current. That's why a transistor can amplify. Question 11.15 is about a different type of transistor, and I'll be explaining this to you a bit further. The input is, it's called a FET, a field effect transistor, and the input terminal is not the base, it's called the gate. The output terminal is not the collector, it's called the drain, and the common terminal is called the source. So in a bipolar junction transistor, which is a symbol we were looking at earlier, that would be the base. In a FET, it's the gate. That would be the collector. In a FET, it's the drain. That would be the emitter. But in a FET, which is what this is, that's called the source. So we have gate, drain, source. Gate, drain, source. The difference between a field effect transistor and a bipolar junction transistor, in a bipolar junction transistor, it's changes of base emitter current that control the much larger emitter collector current. With a FET, it's not changes of current that does the amplification, it's changes of voltage on the gate controls the much larger source drain current. So changes of voltage on the gate control a much larger source drain current. So it is an amplifier as well. So let's have a look at our answers. Output current variations using input voltage variations. It is changes of voltage on the gate that produce changes of current in the source drain circuit. So the correct answer is output changes of current using input changes of voltage. The field effect transistor has advantages over the BJT in that it's a much higher input impedance. That's important because input impedance determines how much power the transistor takes from its source. Whatever's connected to the input of the transistor is called its source. If it's a BJT, it needs current. Wherever there's current, there's voltage. So a BJT consumes power to amplify. P equals E by I. Whereas a JFET, or just a FET, only needs voltage. It doesn't need current. There's no current, there's no P equals E by I, so a junction FET takes very little power from its source. Some sources you can't take too much power from, say an oscillator. If you tried to take too much power from an oscillator with a BJT transistor, you could stop the oscillator from oscillating. So a FET would be used there. Let's go straight on to 11.16. When compared to bipolar transistors, FETs have a higher input impedance. Because they only amplify voltage, because they only take voltage at their input and no current, that means they're a high input impedance, because impedance Z equals E over I. And there's no I, or very small I, so FETs have a very high input impedance. That's their advantage over ordinary transistors, BJT transistors. 1117, the element which forms a similar function to the collector in a junction transistor is called the drain. Let me write down the similarities. The drain of a FET is the collector in a BJT transistor. The gate of a FET is the base of a BJT, and the source lead is the same as the emitter lead in a BJT. Drain is to collector as gate is to base as source is to emitter. So a transistor, this is 1118, a BJT transistor is a current amplifier. It's changes of base current that produce changes of collector current. Now if you change the base current from 10 to 20 milliamps, that's a change of 10 milliamps. And if the collector current during that change of base current changes from 100 milliamps to 600 milliamps, that's a change of 500 milliamps. So the change in the collector current was 500 milliamps, and that was brought about by a change in base current of 10 milliamps. So the gain of that transistor is 10 into 500, the gain is 50. That gain, that current gain, is referred to as the beta of the transistor. And in the next question I've drawn a symbol, the equation. So we might go straight on and have a look at that now. Question 1119, an increase of 1 milliamp in base current in a common emitter transistor amplifier causes the collector current to rise by 100. So the change in base current is a milliamp, and the change in collector current is 100 milliamps. If we divide the change in the base current into the change of the collector current, we get the beta. 1 into 100 is 100. That's what this symbol, this equation here means. This is the Greek letter beta, current gain of a transistor. This is the Greek letter delta, that means change in, and that means change in again. So the current gain is the change in collector current divided by the change in base current. In this question, the change in base current, this one here, the change in base current was 1 milliamp. The change in collector current is 100 milliamps. So we divide 100 by 1 and we get 100. It's a current gain, or beta, of a transistor. Question 1120, it's again about transistors and current gain. Scroll down a little bit. The ratio of the collector current, IC, to the base current, IB, of a transistor is called the current gain, but it's also called the beta. You need to remember both. The ratio of collector current to change in collector current to the change in base current is called the current gain, or the beta, of the transistor. Now remember I told you had to know one mode of operation for transistors and FETs, and that one mode that you have to know is common emitter. I've put a circuit here just to show you a practical circuit of a transistor amplifier. That's the emitter. Sometimes the symbol's shown there rather than here, but it's pointing out. The arrow's pointing out, so that's an NPN transistor. And this is the emitter, this is the collector, and this is the base, and the emitter is common to both. That symbol means earth, and the emitter is common to both input and output, so that's called a common emitter circuit. And that's the only one you need to know. You don't have to know common collector, common drain, common gate. Question 1122, and this is something new that you have to know about common emitter amplifiers, and you only have to know about common emitter amplifiers. If this is the signal this is a common emitter circuit. If this is the input signal into a common emitter circuit, that's a sine wave, which sine wave will we get on the output? Will it be A, B, C, or D? Well, with common emitter, the phase is inverted 180 degrees. So this is the input. It's certainly not this, because that's not a sine wave. It's certainly not that, because that's not a sine wave. This sine wave B is in phase with the input, but this sine wave A is out of phase with the input by 180 degrees. So the answer here is A. I'll write it in, out of phase. And that happens in common emitter circuits. Oops. Might just have to pull that diagram down a little bit. There we are. So this is the input, and the output is phase shifted by 180 degrees, whereas this is going up, this is coming down, whereas this is coming down, that's going up. That's a phase shift of 180 degrees. And you need to know that for common emitter amplifiers. And that's about it for common emitter amplifiers. Let's look at question 1123, which is related to the last question. The characteristics of a common emitter transistor circuit is phase inversion. They're not asking you by how much, but it's actually 180 degrees. And you can see the input signal there, and the output signal is phase shifted by 180 degrees, whereas that's going up, this is coming down, this is coming down, that's going up. That's a 180 degree phase shift. Question 1124, this amplifier is operating as I put a circuit in again. It's only to help you. You're not going to get a circuit like that in the exam. But just to remind you, it's NPN, and that's the arrow symbol pointing out, so never points in, NPN. And this is the middle leg, and the input and output is the base and the collector, and the emitter is common. These are all earth, and so the emitter is common to input and output, so it is a very easy, just a repeat of previous questions, a common emitter circuit. That's the only one you need to know. Remember that. (1125), the term which does not relate to solid-state devices, that is semiconductor devices, is, well, collector does, and you can do this by a process of elimination. A collector is a BJT transistor. Cathode, a semiconductor diode has a cathode. Drain is an electrode on the field effect transistor. Thermionic emission is the process by which metals are heated to the point that electrons are boiled off. You don't need to know that. Well, you might. I'll have a look, see if we've got to do vacuum tubes later on. But thermionic emission has got nothing to do with semiconductors at all. Heat sinks, 1126. Here's a picture of a heat sink. It's a little circuit board, and you can see the transistors there, another transistor there, two transistors, and that aluminium heatsink. The purpose of that is to keep the power transistors or transistors cold. Power transistors get very hot, so we put a heatsink on them, much like putting a heatsink on the microprocessor in a computer. So power transistors require a heatsink. (1127) To assist a power transistor to operate within its temperature range, use is made of a heatsink. Just a cooling fins. If you attach a transistor to this, all the heat from the transistor is going to flow into this heatsink and be dissipated to the air to keep the transistor cool. Well, that's it for tutorial number 14 on semiconductors. We'll be talking more on transistors, diodes and all those sorts of things later on, but for now we just want a very light coverage, and I'd like you to remember all of the things in this tutorial and to test yourself with drill number 11. Thank you for being patient with me, and I'll see you back in the next tutorial. Cheers for now. This is Ron, tt14.